Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the first module of this course, that is the introduction module. And the idea behind this module is to give you a basic introduction to operating systems. So within this module currently we are on the first topic, that is computer hardware review. And in this topic, we are going over the computer hardware concepts once again, so that when we start studying about the operating systems, we have a good understanding of how the hardware works, right? So we said that there are three major hardware components in a computer system. The first one is the CPU, then we have the memory, and then there is a set of IO devices. So in the previous video, we have already talked about the CPU. Now in this video, we want to study the memory. So we'll understand what does the memory do, how does it work, and what is the interface that it exposes to the operating system. So without further ado, let's get started. So let us start the discussion with this basic diagram. This is a model of a computer which shows what are the major components and how are they organized. So there are three major components, as I already said. There is the CPU or the processor, then we have the memory, and then we have a set of IO devices. And all of these major components are connected by the bus, right? So we have already talked about the CPU in the previous video, right? So now in this video, let us look at memory in more detail and have a good understanding about it. So first of all, let us understand why do we need the memory in the computer system. So this is the von Neumann model, which shows the different hardware components and how do they interact with each other. Now the basic job of computing, or the basic idea behind computing, is that we will give some input to the computer. The computer will take that input and process it, and then return the output result, right? So this is how it goes: input, processing, and output. Now the user gives their input via the input devices, and this input can be in a wide variety of formats. It could be a text input, it could be a number, it could be an image, audio, video. So there are a wide variety of options in which the user can give that input, and that input will go and sit into the memory. So this is the place where all the information is stored while the CPU is working with it. So the information that the CPU will process, first of all, has to be stored into the memory. That is why we need the memory. And if you look at the memory, then the information that is stored in memory is of two types. Any information in memory can be classified into these two types. Either it will be a data. So this is the data that the user has supplied so that the computer can process it, right? And apart from data, the other kind of information that we have is the instructions. So the instructions are commands for the CPU, which tell how the CPU should process that data, right? So we now have the instructions and the data into the memory, and the CPU will basically fetch both the instructions and the data. So it will fetch the data and execute these instructions over this data to produce some new output, and that output is also stored into the memory. So while the processing is happening, all the information, the input and output, the instructions and data need to be stored into the memory. And finally, the output that has been produced is transferred from the memory to the output devices so that the user can consume that data. So you can see the memory is the place where all the information is stored while the CPU is processing it, right? That is why we need the memory. So now that we have understood why do we need the memory, let us see how it is organized. So as you can see in this slide, a memory is a sequence of storage locations. So for example, here you see a simple memory that has 8 storage locations, and this is how any kind of memory is structured. It will be a sequence, or you can call it an array of storage locations. The next point about the memory is that with these sequence of storage locations, for every location there is a unique address associated with it. So as you can see here, this simple memory has 8 storage locations, and with each of them there is an address. The address starts from 0 and goes up till 7. So these are the addresses in decimal number system, but in the computer system these numbers will be in the binary format, right? So these are the addresses, and as you can see, these addresses are continuous in nature. That is, there is no gap between any two addresses. So this is how we can reference any particular storage location, because there are several of them, and to reference any one of the storage location you need an address, right? The next point is that the size or the capacity of the memory is measured in bytes. So in the second video of this topic where we talked about the Boolean theory, we said that the most smallest unit of computer storage is a bit, and a bit can store either a 0 or a 1, right? A bit is a very simple storage unit, and when you combine 8 bits, then you get a byte. And instead of measuring the computer storage in bits, it is generally measured in bytes because it's a more convenient unit of storage, right? And whenever you will go to buy memory, DRAM or disk, it will come in let's say megabytes, gigabytes. You will hear these terms, terabytes and so on, right? So the point is that the size or capacity of the memory, that is how much data that the memory can store, is measured in bytes. Another important point about the memory is like the very purpose of any kind of memory is to store data so that it can be retrieved at a later point in time. So the only purpose, the only reason we store any piece of information is that we might need it at a later point in time. So whenever the input is coming from the user, that sits in the memory, because later when it has to be processed, then the CPU will fetch those data and instructions. And this is true for any kind of memory, that you store information so that you can retrieve from it at a later point in time. So now let us look at how the interaction with the memory happens. So interaction with the memory happens using two types of operations. One is called the read, the other is called the write, and they are very simple operations. So reading means you want to get the data that is present at any particular address. So you can see this example, read from location 2. So as you can see, the first of all, the user has supplied the address, and whatever address they supply, the data at that location will be returned to the user. So this is how the read operation works. So in this case, the value 100 will be returned to the user, right? And the other operation is the write operation. Here, instead of getting the value, we want to place a new value into the memory. So as you can see, this write operation is saying write 50 to location 6. So one point is that in while writing, you also have to supply the data along with the address. So in read operation, you only need to supply the address. In write operation, which is kind of obvious, you also have to supply the data. So here the operation is write 50 to location 6. So initially the value 2012 was present at this location, and when this operation happens, that value will be overwritten and a new value, that is 50, will be placed in this location. So this is how the interaction with the memory takes place in the form of reads and writes. And reads and writes are also known as load and store. They mean the same thing. So in the previous slide, we also said that we store information in the memory so that we can retrieve at a later point in time. So now you understand how you can store the memory and then later retrieve it at a later point in time. The final point about the memory is that when we are performing reads or writes on the memory, then the memory unit only sees a stream of data and addresses. Basically, the point is the memory unit does not know from where the data and the addresses are coming, which program is generating that, or from which device it is coming, right? So it is oblivious to the source of the data and the addresses. It only sees a stream of data and addresses, and it is kind of neutral to where it is coming from. So now that we have understood why do we need the memory and how does it function, let us talk about a very important point in the context of memory, that is memory hierarchy. So as you can see in this von Neumann model, we have the memory, and memory is a form of storage, right? We can store data and instructions in it. And apart from the memory, we also have another type of storage, that is the registers. So the registers are on the CPU. The only difference is that they are smaller in size, first of all, and the speed is much higher than the memory. So now the question to ask is that why do we need two different types of storage on the same computer system? We have the memory, right? Why can't we use just the memory? And why do we need the CPU to have their own registers? So that is where lies the motivation behind the memory hierarchy. Let us understand why do we need different types of storage or memory in the same computer system. So to understand why do we have different types of memory or storage, you can say, in the same computer system, let us now talk about what are the ideal properties of a memory, right? So the first property that any ideal memory should be having is that it should have a large capacity. The point is that we should be able to store as much data as possible in that memory, right? Then the next point is that it should be very fast. So when we say fast, we mean that the time taken to do any transaction on the memory, that is reading or writing, should be very less, right? It should be very fast. We can read or write our data at a very good speed, right? So this was the second desirable property. Then apart from capacity and speed, there is the cost. So the ideal property of any memory is that it should be very cheap. So the cost per byte of memory, that is also very important, right? To gain capacity or speed, we should not be spending too much money on the memory. So the third property is that memory should also be cheap. And the final property is that it should be persistent. So when we say persistent, we mean that it should be non-volatile. So generally, memory works on electricity, and electronic forms of memory will lose their data when the computer is shut down or the power goes off. So in that case, whatever data that was stored will be lost. So these types of memory are called volatile. So we do not want memory to be volatile. Ideally, we want the memory to be able to store data for as much time as possible. So that is the final desirable property, that is any memory should be persistent. So now that we have talked about the different properties that we desire from any ideal type of memory, let us talk a bit about, is it possible or is it easy to achieve all of these properties in one single type of memory? And the answer is not really, because if you see the first property, that is capacity, if you increase the capacity of the memory, if you are storing a large amount of data in any memory, then in order to search that memory, it will take some time. So the speed goes down. So capacity and speed are at odds with each other. It is very difficult to build a very large memory with a very high speed, right? Smaller memories are faster and larger memories are slower. This is the rule of thumb. So there is a trade-off that exists between capacity as well as speed. Next, again, there is a trade-off between speed and cost, because to manufacture memories that are very high speed, we use sophisticated technology, and when you use that kind of technology, the cost to manufacture goes up. Take the example of registers. So registers are the fastest form of memory, and they have been designed to support the execution of instructions that the CPU does. CPU can execute millions and billions of instructions per second. So ideally, per second, we should be able to perform millions and billions of transactions on the registers, and that is possible. But the cost to manufacture registers goes up very high, because we use very sophisticated forms of technology for that. So again, there is a trade-off between the speed and the cost that is required to manufacture that kind of fast memory. So as you can see, there are some trade-offs. Two trade-offs we already talked about, that is between the capacity and speed, and then speed and cost. So it is very difficult to achieve all of these desirable properties in one single type of memory, and that is where the memory hierarchy comes into the picture. So the idea is that instead of having one single memory achieve all of these desirable properties, we compose a set of different memories, and each of the memory will be fulfilling some criteria, not all the criteria, but having a set or a composition of different types of memory which fulfill different criteria, we can consider the set as somewhat close to the ideal type of memory. So let us look at an example of memory hierarchy from a computer system. So this is how the memory hierarchy looks like. So this is a very loaded picture. Let us understand this in parts. First of all, the idea is that in any computer system, since we already know that any one single memory would not be able to fulfill all the desirable properties that we just studied. So instead of using one type of memory, we go for different types of memory and compose a pyramid, something like this. So what the pyramid is trying to say, in any computer system, we use different amounts of different types of memories. And the pyramid has this structure that at the top of the pyramid, where the pyramid is narrow, this is signifying that the amount of registers that we use is least. And as we go down the pyramid, the amount of the memory that we use in a computer system increases. So we use more amount of cache memory than the registers, then we use more amount of main memory than the cache memory. So first of all, you might not be familiar with all the different types of layers, but we will talk about these individual layers and these individual types of memory in the next slides. So the basic idea should be clear, that instead of using one single type of memory, instead we construct the memory using a set of different types of memories, and each of these memory fulfills some desirable property, not all the desirable property, and as a set, as a composite set, this entire hierarchy, you can say, fulfills all the properties at different levels, right? So first thing, which I already said, that there are certain properties about this memory hierarchy. First of all, as you go down the hierarchy, then the capacity of the memory increases. This we already discussed, right? The amount of the memory that you use in the computer system goes increases, right? So this was about the capacity. Now let's talk about the other properties of this memory hierarchy. The next point about the memory hierarchy is that if the size of the memory that we use is increasing as we go down the hierarchy, then the opposite will be true for the speed. So the speed will be decreasing, right? For smaller memory there is more speed, for larger memory there is less speed. So this we have already discussed. So the next point is that as you go up in the memory hierarchy, the speed increases. So at the top you will have the fastest form of memory, and at the bottom you will have the slowest form of memory. So you can see the fastest form of memory has the smallest capacity, and the memory with the largest capacity will be having the least speed. So this was about the speed. Now let us talk about the cost part. So in order to increase the speed or achieve higher speeds, we use sophisticated technologies. This we have already said. So as you can see, as we go up in the hierarchy, we are trying to achieve as much speed as possible, and hence the cost per byte of the memory that is at a higher level in the hierarchy will be more. So the cost to manufacture registers will be more than cache. Similarly, the cost to manufacture cache will be more than main memory, and so on. So as we go up in the hierarchy, the cost increases. So this was about the cost. Finally, let's talk about the last property, that is persistence. So memories that are on the lower level are persistent forms of memory, and the primary memory, the registers, cache and main memory, these are volatile in nature. They are built within the computer system, they work on electricity, and these are not persistent. Below the main memory, these forms of memory, that is non-volatile memory, hard disk, CD, DVD, pen drives, magnetic tapes, all of these are persistent in nature. You can say these are non-volatile. Even if the electricity is not there, power is not there, they will store the data. So these memory, that is the ones that are persistent, are used to store data permanently, right? Because otherwise our data will be completely lost if we just rely on the volatile types of memory. So we now understand what is the memory hierarchy, what does this pyramid structure represent, what are the different trends as we go up or down the hierarchy, how does these properties behave. So the final thing that I want to talk about this hierarchy is this classification between different types of memory, that is primary, secondary and tertiary. So as you can see, the top three layers are classified as primary, that is registers, cache and main memory. The two layers after that come into the secondary memory, and the final layer goes into the tertiary memory. So now let us understand what are the differences between these different kinds of memory, right? So the primary memory is required by the CPU for the core execution of instructions. So first of all, these are very fast, right? As you can see, they sit at the top of the memory hierarchy, and the reason they are primary is that they are very fast in nature and they are used for the actual execution of the programs. Now the problem with the primary memory is that it is first of all small capacity. You can see it cannot store a large amount of data, right? And the another problem is that it is not persistent. So it is volatile in nature, and once the power goes off, all the data that has been computed, it will be lost. So that is why in order to supplement the primary memory, we need the secondary memory. So secondary memory first of all is large in capacity. So all the data that we want is actually stored in the secondary memory, and whenever it is required, data is transferred from the secondary memory to the primary memory for execution, right? So this was about the capacity. The other thing is that secondary memory is persistent in nature, and once the computation has been done and we wanted to store the data permanently for longer periods of time, then that data is transferred to the secondary memory, right? So that is how data transfers happen between the secondary and primary when the need is required. And finally comes the tertiary memory. Tertiary memory is used for backup and archival purposes. One of the example that you can see is magnetic tapes. Once the data has been generated and also consumed, and we just want it for backup, then that data is transferred into this tertiary form of memory. So you can see how these different types of memory have been classified depending on the use case. So now that we have a good understanding of the hierarchy, what we will do now, we'll talk about the individual layers in more detail. We'll study about them, what are the properties that each individual layer provides to the hierarchy, and how do they supplement the hierarchy so that the hierarchy can give all the desirable properties as a whole. So let us now talk about the individual layers in the memory hierarchy. So let us discuss the topmost layer in the memory hierarchy, that is the registers. So the way we are going to study each type of memory is that we'll discuss some of the properties, as you can see, some of which are listed on this slide. And by discussing these properties, we'll gain a good understanding of each type of memory. So let us first of all begin by understanding the use case. So we have already talked about the registers in the previous video, right? So registers are used by the CPU during the instruction execution. So recall the instruction execution cycle, and almost in all the phases of that cycle, you need the registers, right? During instruction fetch, you need the program counter. Then in the decode phase, you need the instruction register. And while computation, the operands are stored in the registers. The final result is also written back in the registers. So registers are highly coupled with the instruction execution. So this was about the use case. Now let's talk about the type. So register are classified as primary memory because just now you saw that how the registers are tightly coupled with the instruction execution. So they are classified under primary memory. So this is something that is indispensable and is required for the execution of the programs. Then the location of the registers, as we already know, is on the CPU chip, right? It's the closest to the where execution happens, right? Then the speed, the registers are at the top of the memory hierarchy, so they are the fastest form of memory in the hierarchy. So as you can see, it has written it is as fast as the CPU, right? It is designed to support the execution of instructions, and modern CPUs can execute millions and billions of instructions. So that is the kind of speed that the registers support, reading and writing at that high rate, right? So they are the fastest form of memory. Now let's come to the cost. Again, since they are at the top, they are the costliest form of memory. So in order to support such kind of speeds, very sophisticated technologies are used to manufacture these registers. Hence the cost of registers per byte is very high. Then let's talk about the size. So again, since it's at the top, it's the least amount of memory that you can find in the entire computer system. So registers are used in very small amounts. They are very costly, right? So in a typical computer system, the amount of registers ranges somewhere between less than 1 kilobyte, right? And finally, let's talk about the technology. First of all, since it's a primary memory, it's volatile in nature. When the power will go off, the contents of the registers will be lost. It depends on the electricity. And the technology that is used to manufacture the registers is the semiconductor. So registers are manufactured along with the CPU itself. So the whole silicon wafer is manufactured together. So registers are also part of the CPU. So both of them are manufactured using the semiconductor technology. So this was about the registers. You saw what are the different properties it has. Now let's talk about the next layer in the memory hierarchy. So now let us discuss the next layer in the memory hierarchy, that is the cache memory. So what is cache memory and what does it do? So basically recall that when the CPU is executing instructions, then it has to access the main memory. Either it could be to fetch the instruction or it could be to fetch the data, but memory access happens on every instruction. Now the problem with this is that main memory is slow. To get the data from main memory, it takes a considerable amount of time. So to compensate for that, we have introduced another layer, that is the cache memory between the registers and the main memory, right? So cache memory, as you can see, it is one layer above than the main memory. It is smaller than the main memory and has a higher speed. So now what happens is that data that is frequently required or accessed is transferred from the main memory into the cache memory. And now whenever the CPU has to transfer data from the main memory to the registers, first of all, it will not go to the main memory. It will look in the cache. If the data that it is looking for is found in the cache, then it is called a cache hit, right? In that case, the data was made available to the CPU in less amount of time because cache memory is fast, right? So we don't have to pay the penalty of memory access. So this is the good thing about the cache hit, that data was quickly available to the CPU. There would be times when the data would not be found in the cache. That is called a cache miss, because as you can see, the size of the cache memory is smaller than the main memory. So all the data we cannot fit in the cache. So in that case, when the data is not found, when there is a cache miss, In that case, the CPU will go and get the data from main memory. But the idea is that cache hits are more than cache misses, right? That is the property of a good cache. So in the common case, the time that it takes to get the data is much less as compared to the previous case when we were directly going to the main memory for every data access, right? So this is the idea behind the cache memory, to speed up the execution of instructions, because if we rely only on the main memory, then the instruction execution speed will become very less because main memory access is slow. So that is where the cache memory supplements the main memory. So now that we have understood why do we need a cache memory, let us look at how does it look and what are the different properties of cache memory. So here you can see we have a CPU chip and there are 4 cores. This blue region is the core. On every core there is one L1 cache, an L2 cache, and then on the entire chip there is a L3 cache which is shared by all the cores. So the L1 cache and L2 cache is private to each core, and then we have a shared cache which is shared by all the cores. So first of all, let us understand what are these 3 different levels of cache. So till now we have assumed that there is one single cache memory in the system, but as you saw in the previous diagram, there was L1, L2 and L3 cache. So what was that? So the thing is, caching is such a good idea that memory designers decided to have not one but multiple levels of cache, and the number of levels range somewhere 2 to 3 levels in a computer system. So instead of having this one single layer, the picture looks something like this. So there is one L1 cache. I'm assuming that there are 3 levels of cache. So there is one L1 cache, then L2, and then L3. So all of these, first of all, are cache memories only. It's just that as you go from L3 to L1, the size of the cache memory is decreasing and the speed is increasing, right? The closer the cache is, the faster it is and smaller it is, right? The idea remains the same. So whenever the CPU needs some data, now first of all it will look in the L1 cache. If there is a cache hit, then no need to go any further. If there is a cache miss, then it will go to L2. Again, if there is a hit, then the data is returned from L2 cache. Otherwise, if there is a miss, then it goes to L3 cache. And finally, again, if there is a miss, then only you go to the main memory. So now you see that the likelihood of getting the data in the cache has increased. It is very less likely that you will be going to the main memory. In the common case, the data will be available from the cache memory, and thus the time that it is taking to get the data has significantly reduced by introducing this multiple levels of cache, right? So this is the idea behind having multiple levels of cache, that the CPU does not have to go till the main memory, right? So this speeds up the execution of instructions also. So this is the idea behind having multiple levels of cache. So now that we have understood what are these different levels of cache, let's talk about the properties of cache memory. So first of all, it is obvious, it is classified into primary memory because it is used during the execution of instructions. The data that is required by the CPU, that is looked into the cache. So it's closely involved in the execution of instruction. It's a primary form of memory. Then the location is the CPU. So as you can see, the L1 and L2 cache are on the cores, the private cores, and the last level cache, that is the L3 cache, is also on the CPU chip and shared by the different cores. The speed, if you talk about the speed, it's much more than the main memory but slower than the registers. So it's between the registers and the main memory. So the speed is basically decided by the position of the memory in the hierarchy, right? And the cost, again, the cost is not as much as the registers, but it is still very high. And let's talk about the size of the cache memory. So the L1 cache will be smaller than the L2, and L2 will be smaller than the last level cache, that is L3. So these come in different size ranges. So L1 cache can range some between some few kilobytes, and L2 cache will be in some few megabytes, right? And finally, let's talk about the technology. So the technology that is used is called SRAM, or static RAM. If we compare this with the main memory, then the technology that is used to make the main memory is called dynamic RAM, right? So these are different semiconductor technologies. And again, the cache memory is volatile in nature. It's on the CPU chip. It depends on the power. And whenever the power goes off, its contents will be lost. So this was about the cache memory. Now let's look at the next level in the memory, that is the main memory. So now let us talk about the main memory. It's the most important form of memory in the computer system. So basically, all the data that is arriving from the input devices, first of all, it sits in the main memory. All the data and the instructions before any processing can begin is first of all stored in the main memory. And even when the processing is taking place, then main memory is accessed, that data is transferred to the cache and then to the registers, right? Then the CPU executes those. And after execution, whatever data results and output has been produced, that is also kept in the main memory before it is sent to the output devices. So let's talk about the properties of main memory. So as you can see, the main memory is classified as primary memory along with the registers and cache, because all of these are directly involved in the execution of the programs. Then let's talk about the location. So the main memory is located on the motherboard. So till now we have seen that registers and the cache are present on the CPU chip itself, but the main memory is a separate hardware component and it is present on the motherboard. Then let's talk about the speed. So main memory is still fast. We said that the main memory is slow, and that is why we need a cache memory. But if you compare this with the very slow secondary memory and tertiary memory, it's still fast. Then the cost of the main memory is high. It's not as high as the registers or cache, but it's still high if we compare this with the size of the secondary memory. And the size, so main memory comes in the range of gigabytes. Typical main memory sizes include 4 gigabytes, 8 gigabytes, right? Common computer system have DRAMs or main memory in this size range only. Then the technology that is used is called the semiconductor dynamic random access memory. So what does it mean, random access memory? It means that the time that it takes to access any memory location remains the same. So you can randomly access the main memory and it will take the same amount of time. So it's different from the cache memory because it's dynamic RAM and the cache is static RAM. So both are semiconductor technologies. And finally, the main memory is volatile in nature. When the computer system is shut down, the contents of the main memory will be lost. So this was about the main memory. So now after talking about the main memory, let us talk about the secondary memory. So we'll talk about both the non-volatile memory and these hard disk, CD, DVD, pen drives together as one single secondary memory. So let's talk about the secondary memory. So basically, secondary memory is used to supplement the primary memory because it has some drawbacks. The primary memory is, first of all, has limited capacity and it is also volatile in nature. So to compensate for these things, we need the secondary memory to, first of all, store large amounts of data, and that too permanently, right, for long periods of time. So that is why we need the secondary memory as the persistent storage for the computer system. So now let us look at some examples and properties of secondary memory. So you can see here we have several examples. The first one is the solid state disk or SSD, and it is also called non-volatile memory. Then there is this hard disk drive, and then we have CD, DVDs, and finally the portable format, that is the pen drive. So these are some of the examples that are included in the secondary memory. So the type we already know, it is secondary. Let's talk about the location. So there are two options. Either they come as embedded on the motherboard. So sometimes the SSD or SDT are part of the motherboard, right, attached on the motherboard, or they come as external units. So basically, when it is external, it has to be inserted into some slot into the computer system as a peripheral device. So if you have used the pen drive or the CD, you know that it is external to the computer system, right? Then let's talk about the speed. So one of the important characteristic of the secondary memory is its large capacity, right? It is used because it can store a large amount of data. So when the capacity is high, then you can expect that the speed will be slow. So that is why the speed of secondary memory is very low, and these cannot be used directly for the execution of programs. So data has to first of all transfer from the secondary to the primary memory, which is quite fast, right? So that is why primary memory is used for execution of programs, and when the data has to be stored, then only secondary memory is used for long-term storage, right? Then let's talk about the cost. So secondary memory is very cheap. That is why it is the option, it is the preferred option to manufacture large quantities of memory, right? So the capacities of memory, as you can see, it can range from few gigabytes to several terabytes. Since it's cheap, that is why it can be used to manufacture such large quantities of memory. Finally, let's talk about the technology that is used. So there are different types of technology that come under the secondary memory. The first one is the flash memory. So the SSD or the pen drive, these are manufactured using the flash technology. This is again a semiconductor technology, but different from the DRAM. or the cache memory. Then there are certain memories which is mechanical in nature. For example, the hard disk drive. Mechanical because here we have a motor which rotates, so there are moving parts. That is why this is a mechanical technology. Then there are certain memories like CD or DVD which are classified as optical because they use light for reading or writing. And then the final thing is that they are non-volatile, that is they are persistent forms of memory. So this was about the different properties of secondary memory. So now let us talk about the last layer in the memory hierarchy, that is the tertiary memory. So these are not that commonly used nowadays, but nonetheless in industry sometimes they have to back up or archive their data. In that case they use the tertiary memory, and one good example is the magnetic tapes. So let's talk about the properties of the tertiary memory quickly. So the location is obviously external. They are not part of the computer system in any way. They are external units that have to be attached to the computer system. The speed is very slow because you don't need to use them every day. These are very cheap first of all and can store a large amount of data and are very slow in speed. So we talked about the speed. The cost, as we said, is very low and they can store large amounts of data. That is why they are used for backup and archival. Finally, the technology, as the name says, it's magnetic in nature and these are persistent forms of memory. So this was about the tertiary memory. So now we have discussed all the levels in the memory hierarchy, and all that we discussed in the previous slides, I have summarized it into this table. So you can see the different types of memory in the first column, that is registers, cache, main memory, the secondary memory, and magnetic tapes, and all the attributes associated with these types of memory has been summarized in this table. You can refer them if you need it. So the final thing that I want to talk about is how all of the memory components interact with each other when the computer is doing its job, that is executing the program. So first of all, you can see this is the computer system. We have the CPU, there is the execution unit, then there are the registers, then there's the cache memory. I have only shown one level for the sake of simplicity. Then outside the CPU, you have the DRAM, and then the secondary memory, that is the hard disk drive. So the way this works is that first of all, you observe that if you go from right to left, then the size is decreasing and the speed is increasing. Basically, it's the order of the memory hierarchy. The registers are at the top of the hierarchy, right? So this is the order in which the memory is organized in the memory hierarchy also. So when you boot up the system, at that point, the registers, cache, and DRAM is empty because it is the primary memory and it is volatile in nature. At that point, there will be no data in these memory units. So first of all, the data has to be transferred from the secondary memory, in this case, the hard disk drive, to the primary memory. So first of all the data and the instructions of the program are copied to the DRAM. Once it's in the DRAM, then the program execution can begin. So first of all, the CPU will try to load data from the memory to the registers. For that, it will look into the cache. Since the cache is empty initially, it will be slowly populated by copying the data, frequently used data, from the DRAM into the cache. And when the program is executing, then most of the data will then be found in the cache, right? So this is how the registers, cache, and DRAM will be used when the program is getting executed. And whatever data is produced in the registers, it will be copied to cache and slowly to the DRAM. Finally, when all of this is done and it is time to store them persistently, the data will be copied from DRAM to the secondary memory, that is the hard disk drive. So if you observe, when the data has to be populated, then data travels from right to left. That is, it goes up to the memory hierarchy as close as possible to the execution unit. And finally, when it is time to store the data, then the data travels downwards in the memory hierarchy from left to right. And finally, the data is stored in the secondary memory where it is stored for long periods of time persistently. So this is how the data flows between different components of the memory hierarchy, and this is how the memory hierarchy works. So guys, this was it for this video. In this video, we talked what does the memory do and how is it structured. Then we talked about what are the ideal properties that a memory should have. Then since a particular memory, one single memory, cannot achieve all these properties, we saw that we need a memory hierarchy. And finally, we looked at the different layers that are part of the memory hierarchy. And in this final example, you saw how all of the memory units, different types of memory in the hierarchy, interact with each other. So this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.